Hello, how's it going? So the title of this video is a bit clickbaity, right? I do think that concurrency is good, but here I just want to talk about some different types of concurrency so that especially beginners can start to think about which types may suit their project best. So we all know that our computers have all these threads. It doesn't take much of a leap in logic to determine that using them is good, otherwise we're leaving performance on the table. But there are different ways of doing concurrent programming. One of the simplest ways of doing concurrent programming is not to do concurrent programming, but to sort of fake it. So the typical task or the typical situation is, let's say we have a whole lot of jobs that need to be done. It's very tempting to spawn a whole bunch of threads and assign one job to each thread and then let that happen and get the result. But there are situations where it could be useful just to, instead of doing all those tasks in one go, in one big while loop or something, to just pick each task one at a time, perform it, and then move on. A practical example where I use this is in my resource loading for a lot of my handmade games. I'll have a task which loads an image or a resource or something, and I will just keep doing that, like one resource at a time, and return whether the resource was successfully loaded. This has the benefit of making the program seem more responsive, even though there's more overhead in doing each of those individual jobs, rather than just all together in one block. It lets me update a progress bar so that rather than waiting for 30 seconds for the program to run, I can actually see how it's progressing. Even if that ends up taking 45 seconds, it feels snappier. Another option for concurrency, which sort of isn't really concurrency, is SIMD. So let's say that we have some section of logic which can very clearly be expressed mathematically, and it sort of comes down to transforming one set of numbers into one other set of numbers where the same calculation needs to happen to every element. We can group these numbers together into chunks. Now, in the diagram here, I'm picking 4 numbers per chunk, but SIMD, we can have SIMD 256, which lets us have up to 8 numbers per chunk. Some CPUs will even support SIMD 512, although I've heard it's a little funky under the hood, but the option's there. What we do is we grab that chunk, and then every number in that chunk is referred to as a lane. So in this example, we've got 4 lanes per chunk. Then we apply some SIMD operation. It can be a square root, addition, subtraction. There's a whole lot of these different operations, and it will more or less do that whole chunk in one go. So in the same cycle count that it would take to process one floating point number, we can process 4 floating point numbers or 8 floating point numbers. SIMD is really good for these straightforward transformations. It starts to break down a little bit if we need to take the results and boil them down into a single number. So if we can do the parallel work, that's fine, but then if we need to get a single result from that, that can be pretty expensive, but it's an option. The next step on our hierarchy is something I like to call, well, honestly, I call it a CPU shotgun, or you could call it a processor shotgun, and that is where you haven't got really simple deterministic operations like just add a whole bunch of numbers together, but your job still breaks down into like n tasks where each task does not depend on the other task. And these tasks could even be collections of really small tasks. So let's say that we've got 1,000 things that we need to do. We want to break that into 100 tasks. We can group 10 things per subtask or something like that. Think of it as regions, like we're partitioning the space of our job. In this situation, the parallelism is actually really good because we have a well-defined start point and an end point. C++ has something called a parallel for loop, which handles this pretty well. Task flow, a library I'll talk about in a second, also has a really good parallel for, and this is the same logic as the way a compute shader works. So that's another option if we want to keep our result on the GPU for later use. And now I talked about task flow a second ago. So another way to define this is, let's say we have got complex tasks, but some of those tasks can run at the same time. They're not going to interfere with each other. So let's say we've got some task A, and task A is going to use all of the system resources. Like, it would be a nightmare to synchronize this thing. Well, we can just set that down and say, okay, that's task A, but then after task A, let's say we have tasks B and C, and B and C can actually run at the same time. They aren't going to cross over with each other. So we can actually just specify that B and C have to run after A. Maybe they do for some reason, but they can run together. The language of a task graph is actually really expressive. And within these tasks, we can also use parallel for loops and SIMD and all of that stuff. So if task A is a really heavy task, we can still break it down further. So one of the traditional approaches in multi-threading was to have what we call persistent threads. And they are dedicated threads which only do one thing. Like, let's say the classic example is we have a video game world. It's going to have a main loop that updates, performs all the logic and physics and stuff like that. And then we're going to have the job of displaying the world. Now, these two tasks could run with different frequencies. Let's say we want the physics update to happen with a really small delta time. So we want that operation to happen a lot and happen very quickly. Whereas rendering the world, if we go faster than our monitor's display rate, we are burning power, we're wasting power. So we might want to have that operation running at a different frequency. So this persistent threads model is basically saying we'll have two threads and they run forever, and they have some shared resource. So after the world updates, it sort of saves some representation of itself into some common data structure. This could be a synchronization object. This could just be a shared object, which is still, it has to be protected by a semaphore or something, but it's a little more lightweight. And then the render operation will be continually sort of fetching that shared resource, reading it, rendering with it, all of that stuff. So this is a classic approach, and it's still really useful in well-defined situations. However, it does not scale very well. So if I work out my game logic and I work out, there's a certain number of tasks which can just be split off completely independently, run under their own steam, but then 2 years down the line, the new Ryzen Threadripper drops, which has like double the thread count. Well, that doesn't mean that my game is going to be able to take advantage of all that extra horsepower. So this is a situation where a more data-oriented approach or a more flexible approach would scale better. But, it's there, it's an option. It's really good for well-defined situations, and yeah. And look, these approaches are just a few suggestions. There are many more things we can do. But the last one I'm going to give is a more modern approach, the way things are done. This is the producer-consumer pattern. So let's say we have threads, and these threads are general worker threads. They can execute any sort of job. Jobs are defined in a way where they upfront declare all the data which is needed to perform them. And we have some queues. So we have some sort of thread-safe queue where we can push on a bunch of jobs which need to be done. And we have a bunch of threads. They could be waiting in a holding pattern like a spin lock, or they could be asleep or something. And they fetch things from the queue, execute those jobs, and then they pass on messages that the jobs were completed, which can then be read back by the system and responded to. So this is a more modern approach that a lot of game engines will use. So like I said, it was a little bit clickbaity. I do think concurrency is good, but it is important just to be aware of different options and to weigh things up, because there is definitely a cost to be paid in debugging. I'll say that. Here's a handy metaphor to think about it. Threads are like cars. They're easy to start. Driving, yeah, it's easy enough, you can do it. They're hard to stop. So if I were to give any practical advice, working out ways to stop threads and coordinate them that way, that's probably the hardest part of any multi-threading thing. But yeah, that was it. As always, have fun, happy programming, and I will see you soon. Bye.